We continue talking about the Kalman filter, and we do a specific example is the autonomous vehicle tracking the pedestrian on the road. How to do that? Last video, I hope you understand how we derive the formula. We add the noise vector, we add the covariant process noise into the update covariant, right? Uh, in all video, I always remind the last video. I hope you remember, understand when you read the new video. And before we coding in the C++, I hope you know how we derive that. I will just recap quickly and what we do last video. We had to go two step right here, prediction step and Kalman filter step. In prediction step right now, we have the noise vector, the process noise and the motion noise right here. So we already got that value, right? We in this prediction state, we already derive this state space from the motion line, the linear motion model, right? And for the state vector to the position and to the velocity, right? And we add motion noise into the state variable, right? And we derive the motion noise right here, right? And we also derive the covariant matrix, right? Process covariant matrix right here, and we add to this one into the Kalman filter to solve the problem, right? And that's in the process in the prediction phase. In the measurement update, we also know three things. The first, measurement vector z we got from sensor, right? The second, measurement matrix, what the measurement matrix in this case, and what the covariant matrix are in this case. Why? We go back to the Kalman filter. You look at why we need that. In the Kalman filter, we need R, right? We need H, right, to calculate, right? And we need a Z, the measurement vector, to calculate the update measurement, right? So I go quickly. This one, I don't want to remind too much right here. And we had, but what is Z? Z is the measurement vector from sensor we already have. H right here, and Z we got from the LiDAR sensor. LiDAR sensor, we give us the position PSPY. And how to object detection, I talk another video about the LiDAR point cloud topic, okay? And what the H right here? H right here, you had to know we have a measurement vector Z, the 2D, right? We have state vector right here, 4D. So what the measurement matrix mapping between two vector? So right here, what the measurement matrix, we can guess that's this matrix, right? Because 2 times 4 right here, you have the dimension of the H matrix 2 times 4 times 2, 4 times 1. It means 2 times 1, right? I think you understand that. And what the R matrix right here? R matrix right here, the 2 dimension, right? And they have the same dimension of the Z vector because they put, you remember the dimension we put into the same metric. And right here, the uncertainty of the equipment we got from the manufacturer, right? Easy to understand, right? Okay, we're tracking the pedestrian with the state vector for the dimension. It means to the position and to the velocity, right? And okay, that's recap what we learned last video. Okay, we got the new covariant matrix right here for update the new covariant, this process metric, right? Okay, and one here is the state matrix, right? Frequency matrix right here. Right here, just have you to do the code. And okay, go to the code. Before we go to the code right here. I just want to remind you the easiest one for 1D first, right? For 1D dimension first. Alright, so right here we have the examples. Really, the easy example right here. How we know the prediction the 1D dimension. Okay, apply the Kalman filter. I hope you know how to include the Eigen library into the Visual Studio 2019. It's really easy. If I will attach the link, download the Eigen library, and after you download it, you just add into the project. You do it right here. Go the setting. Go to right here, general. You add the Eigen library into here. That's it. That's the way you ask Eigen library. Eigen library help you to calculate linear algebra, multiply, transpose, inverse, something like that. And how it works. Okay, I will show you really basics how the Eigen library help us. If you don't know, you can read the link I provide you. They tell you detail how to use Eigen library. For example, after we include the Eigen vector, okay, we declare the name right here with the Eigen column and vector and matrix right here, okay. And how to get some really basic example to know. For example, I say vector is the for example my vector, okay. They have dimension right here, and you see you can say my vector in about 3, 4. Okay, okay, and you can see how the vector. How about the matrix work? Now the matrix, you say the matrix. The name right here, you can create any name you want, right? You can say any name right here. Matrix D, matrix. Okay, for example, 4 times 4, 4 column 4 row. Okay, my matrix 2, 3. We just take any value you want. And the last row. Okay, we can they will show you. I really will understand it. Same really will example or some basic example how the Eigen help us. Mm. For example, we call the transport. Okay. Let's see there the transport. Let's see the we got the inverse matrix. How we got the inverse matrix? Okay, that's something really basic thing for you. You can learn, go to detail, multiply or divide something like that into the link I give you how to use the Eigen vectors, Eigen library. Okay, here's results, right? And this is my vector. They bring out the vector matrix right here, and I got the inverse matrix. I got the transpose matrix. Okay, and right here I got the inverse matrix. It kind of this Python. Okay, so I hope you understand. I give you a link. They teaching you how to detail you the Eigen library. So that's it. So come back to the 1D dimension Kalman filter example, and right here in the main, that's all. This one may declare the initial value. Okay, in the this is the variable 0 0. Okay, and the matrix right here, this covariant matrix for initial. So we have the covariance. The right here is really big. So we the first time we don't know exactly. Okay, we just sum the 1000 and the motion noise 0 0 right here. You see, we do not ask the formula we already calculated last time. We just say the value right here 0 0 for the process covariant right here, and the motion noise right here 0 is have. I hope you understand. I try to make from very basic and to advanced. I hope you really understand. Okay. And And right now we create the matrix vector right here, single measure. It means single measurement. So we add the 1, 2, 3 value right here into the measurement vector. Right here we don't know what the measurement from sensor. We create that and we try to run the Kalman filter right here, and the Kalman filter will give us the answer update and of the measurement and prediction, right? For the okay, for the Kalman filter, standard Kalman filter. So how this work in this sample really detailed, so you have to do this work. Okay, it's easy, right? So right here we call remember last I show you how the Eigen library help us. You call the we define the SP, or that's the variable, okay, and after that, in the more important thing right here, how you write the Kalman filter function. Any current function you know we had to given the argument right here and the state variable and the covariant, it means the bus by reference, right? Okay, and we into right here we got vector measurement right here. Okay, for example, in the measurement vector right now we have 3 value, 1, 2, 3. We already asked right here, but and we run all the dust measurement and we run the Kalman filter formula right here. Okay, you see, for the measurement update, and we print out the result, and the prediction, we print out the prediction right here. Very simple. I think you easily understand the Kalman filter. And anytime you read the bit application, you when for example autonomous vehicle, you read the Kalman filter part, you easily understand quickly how the people do that. Okay, let's run the program. They run quite slowly. Okay, let's see the result. In this sample, I want you to understand how you write the Kalman filter. That's it. And in next example, we write the program in the ops. I mean, our oriented object programming is a little bit complex. So I don't jump to the oriented object programming. It's quite hard for beginner. Maybe your computer runs faster than mine. Okay, that's the result right here. Oh man, it's really slowly. We have the update for each day. Okay, from initial, like we after first measurement, we update the value right here. Okay, 1. So we Okay, where that? Okay, the first measurement is one. We update the value and we prediction the value something right here. So pitch uncertainty. So after the second measurement, we update the measurement right here and we prediction the 2.999. And after the third measurement, we update the value 2.9 and the prediction 3.999. Right. Right here you can write you add any the measurement you want, run the three values into the measurement list. So that's it. Okay, we I hope you understand the basic code right here. You can type in, I will upload all the code right here to the link. So you go to the link, download it and practice it. Okay, and to the another example I want to show you. Here's the example we talked into the last video. We talked about the tracking the pedestrian is for the dimension to the position and to the velocity. Here the TFT file. This file they show you the value we got it from sensor right here, the fusion sensor. So we have to cap the value laser or error is laser or radar. Laser you have position it as position y and timestamp. We had to need the time right here for it for between the two measurements for the laser to calculate the delta t, right? And the radar data right here, I tell you later what the value right here means, because the value right here is a polar, so in the polar coordinate system. But another example we show that. So today we just focus on the laser data right here and how we use that data into the Kalman filter. I hope you understand this one. It's really important. And right here we have use the Eigen library too. And right here we had to create the three class. First time the measurement package class, and the second the Kalman filter class, and the last one the tracking class. Tracking class is how you use the Kalman class to track the state of the pedestrian, right? The measurement package right here does only help you to get the raw measurement from the TFT file, and we what the cap the data you need to use right here. Maybe you say I need the raw measurement from the laser, I need the measurement from radar, right? The measurement package, and also we got the timestamp, in the test file to calculate the delta t between the two measurements, right? So the important thing right in this code is I hope you try to understand how people write the Kalman filter right here, because the Kalman filter right here at the time we use this matrix for the 4-dimension 4x4 right here, the state transition matrix and the covariant matrix. Okay, so it's quite a little bit complex in this example, and I hope you know about the object-oriented programming and you can understand easily. It's not something, if you already know object-oriented programming, it's really easy to understand. Okay, that's the destructor constructor and into the class. And the more important thing, you understand the prediction function and the update measurement function right here. Okay, thus we declare a variable for Kalman filter as big F, Q, or H, all right? Okay, how we write the Kalman filter function class? You see the header file. Okay, we already I showed last time. So in the two CPP file, we have to write the function prediction. Prediction just copy the formula and put it on, right? That's right, easily, right? And if in the update function, update the measurement sequence, so use the formula and just put everything to the formula, right? The formula, okay? This is quite familiar with you. Okay, there's nothing hard right here for you to understand. So, and after we already have the class Kalman filter, right now how we use this class for tracking the pedestrian, we create the class tracking right here. A tracking right here, you see, we call the object the Kalman filter right here and measurement package. So right here, the more important thing is the function right here, the process measurement. Process measurement, in the process measurement, we will use the Kalman filter, and we use the value from measurement from the sensor to get the answer, right? To get the results for the update and the prediction state. And right here we have the noise right here, acceleration noise. You remember in the formula we have the AS and AY, right? The noise. And we define the Kalman filter KF right here. You see, we use this class to help us to solve the problem right here. And what the tracking CPP file, right, look like. So in the tracking CPP file, you see, we declare the initial value, right? We have the right here, the state vector right here. I want to stay tracking the pedestrian with the first with the 4 dimension. Okay, vector the 4 dimension right here is included to the position and to the velocity, right? And covariant matrix, you remember covariant matrix, but right now is 4 by 4, right? And this initial value, we assume the value right here with the covariant right here is a little bit 1000, right? And after many the iteration, you see this value will change smaller, right? Okay, and continue. We go to the R matrix from the measurement covariant from the equipment, right? That's the sensor errors, uncertainty. You can guess value. Another example, you can see this very different from the manufacturer, right? Okay. How about the measurement matrix? We talked in the first video about the measurement matrix. Okay. How about the initial transition matrix? We can derive last video, right? In the first video, if you don't remember, go back and see it. And noise right here for the S and Y. See, we assume right here the phi. And right here in we write the constructor. So right here in this measurement, this function measurement right here, okay, it's really important for the measurement. We got in initial location and the zero velocity. At some we don't know velocity, we say 0, right? And we got the first value and second value into sensor. Okay, and this is stamp right here. We need to timestamp to calculate the delta t right here. That's the delta t. We calculate the delta t in the two measurement. We got this value from the TFT file, right? Okay, microsecond. Okay, for the Q, how we calculate how we got the matrix covariant matrix Q right here. You look at it, it's really complex. So right here we calculate follow up the delta t. So we call delta t 2, 3, 4 right here. And let's go back to look like. You see, that's the delta t right here, including delta t and the sigma AS, sigma AY into the Q. So it means delta t 2, it means delta t power 2. It means equal delta t to the t. And we create the delta t. I think you easily understand right here from here to here, right? Let's plug it into the formula, nothing difficult right here. Delta t4 is mean right here. It means delta t power 4. Nothing different right here. Delta t power 4, delta t4. It's help you simplify the formula into the code. And we call the KF right here Kalman filter predict. We call the function KF measurement update. That's it, and we print it out. Because right in the tracking CPP, we just call the class Kalman filter, and we use the prediction and update, right? Why? Right. That's it. Right. Look at the Kalman tracking header file. You see, we can create the Kalman filter right here. We use the class right here, right? And into tracking, we just say kf.predict or kf.update, and let's bring to result quickly. And in the main, see, I just explain you what the value into the test file, right? And right here we read about three value into the test file. It's allowed. I can run all of them. I just read the three measurement and bring in the result. Just show you how it's like. You can play with it in your computer. Yeah. Right here, you see, if sensor, we use the measurement bucket right here. You see, if sensor is L, it means we use the laser measurement, right? You say we use the value of the measurement right here, right? From laser, we don't use the radar. Right now, we just only focus on laser. Later, we got the radar later. Okay, that's a reason. There's a fusion sensor, so we combine two data from two sensors. Okay, I didn't capture the data from two sensors, so we got the value S, Y. We read the value from the file. I think you know how to read the file, TXT file, the value from TXT file. So the timestamp, and we push back all that value into this vector measurement packet list. We don't need, we right here we just say the vector measurement packet list, right? And we read the file right here, right? I hope you understand that. Okay. And we say we call the class measurement package, right? So, and we say the object measurement package, and we say measurement type sensor, and measurement package sensor type laser, measurement package draws measurement, right? I go back to see how your measurement package look like. What they include in the measurement package is timestamp, raw measurement, and center type, right? And let's use them. Okay, we just say measurement package dot center type or raw measurement, and we got the value. We did the value from the TXT file. Okay, we push back all the measurement package, the file right here, the value right here into the measurement package, right? And after that, we call the tracking. Okay, create tracking is in the main, and okay, from that we call the tracking process measurement. That will print out for you all the result, the update and measurement update. Okay, that's it. That's all you need. It's really easy. We just create the three Kalman filter object and measurement packet tracking, and we call into the main, print it out. That's it. Really easy. If you don't understand, just download and read again. I hope you understand this one, because in the next video we combine laser and data radar value. Okay, let's run it. Okay, that's the results. Because right here this is a lot of data right here. We only need about three value, 1 through 3. Okay, we predict. They print out for us the prediction right here. Okay, after the first measurement. Okay, prediction, which you see the predict the 11.711.209, right? It's really close, right? And they predict the second measurement 1.61. Look at it, 1.6. Okay, and continue. They predict to the not only the position but also the velocity for you too, and continue the test value at 2.1, right? 2.188. It's really close, right? That's you see how they prediction state variable prediction, right? It's really good. Let's try to write out by yourself and play with the code. And you will understand how to apply the standard Kalman filter for the laser. Just a laser, they give you the Cartesian coordinate, the value in the Cartesian coordinate system. So you use Kalman filter, right? In that time, we use the radar value into the polar coordinate system. Polar coordinate system is right now we have to know that's in the linear motion. We go to the curve, the circular motion, so we have to use extended Kalman filter to apply non-linear motion, right? See you next video. Oh, forgot it. Somebody, I really want to share with you the book. This book really nice. This book really, I think, this book really useful for people learn to computer vision. And about 1,000 pages the computer vision, and I think necessary for you to know about computer vision, how to analyze the picture, how to use the key point and descriptor into in the picture. For the next video, I will tell you how to something about the camera computer vision, how to build up the CAS system, collision avoidance system, and how to calculate the time to collision for the CAS system. Use the LiDAR data and camera, right? We use all the code in the C++, the computer vision in the C++. We analyze the picture in the C++. So that's the reason I want to share this book. This book for all of you to follow the Kalman filter and subscribe my channel. Okay. Okay. You can see the detail into the comment below. Thank you.